Okay. Um, going to give you a big population problem. Where we've got 50 fish after 7 days and 80 fish after 20 days. As I assume an exponential model, you can obtain a formula population P versus time T. Okay. We got our quiz. The first thing you want to do when you're trying to do an exponential model is you want to sketch a graph showing the information that you have. Okay. So start out by sketching a graph and then sketching an exponential curve. Now, it doesn't have to be a perfect exponential curve, but everybody knows how to construct an exponential curve in a window. Okay. Everybody's good at that. So we go ahead and say, okay, maybe our curve looks like this. It's a reasonable shape of an exponential curve. Now, of course, we could always construct it in a window, and I'm going to do that in a few minutes. Okay. But right now, we're just trying to put our information into a window where we know what T and P are at each of these points. So that's the first step. Second step, write out y equals AB to the T. That's the form of an exponential function, general form of an exponential function. And you got to know the general form of every possible function. Now, we're going to be spending a lot of time, some next week and some in the last, the rest of the class pulling things together. Because at this stage, we want to be able to do an exponential model. That's what the homework assignment was. Okay. If you didn't get that done, well, get it done. Okay. Get caught up. It's not that difficult. Okay. So there's a form. Could be A, B to the T, and you could use X instead of T. But since we're dealing here with time, we're going to use T for the variable. It doesn't matter what you use for the variable, as long as you understand that the power here represents your horizontal axis, okay? Represents like your X values, or in this case, your T values. Other forms, AE to the KT, is another common form. Or even y equals 2, a times 2 to the kt. Because here you're just back to your basic toolkit function, and you see that there's a horizontal compression and a vertical stretch. Okay. Right now, we're just going to deal with the AB to the T form. The form is going to be P equals AB to the T. Now, if T equals 7, then P equals 50. So putting that information into this form, we get P equals 50. We don't know what A is, we don't know what B is, but we have the value of T. 50 equals AB to the 7th. Make sure we're recording. And then if P equals 20, then P equals 80. So 80 equals AB to the 20. Again, substituting our value of T and our value of P, we get this equation. These two equations form a system of simultaneous equations that we can solve. Now, we're not going to be able to solve these by elimination. Can't add a multiple of one to the other to get rid of either A or B, because A is multiplied by B to a power. Unlike with linear equations, where you have a multiple of X plus a multiple of Y equals whatever, you have two of those equations, you can eliminate a variable, okay? And that's something we learned to do back in chapter 2. We also learned to graph two simultaneous equations. So we're going to be talking about that. It's kind of the next thing we do. All right. For now, we have two equations, two simultaneous equations in A and B. So I'm going to rewrite them. It's not AB to the T, it's AB to the 7th. And AB to the 20th. I'll number the equations. Not everybody does this, but often they're numbered one way or another. I just use a circled 1 and a circled 2 for equation 1 and equation 2. Okay, so what do? We solve one of these equations. Generally, we solve one of the equations for A and plug that result into the other equation. We're using substitution. So we solve substitution. First, solve the first equation for A. We get A equals 50 over B to the 7th. Just divide both sides by B to the 7th, and we've solved for A. Very simple equation to solve for A. Now we're going to get an equation to solve. It's not quite that simple, but we'll be able to do it. So there it is. And we substitute that into equation 2. equation 2 is 80 equals AB to the 20th. A is 50 over B to the 7th. So this is 50 over B to the 7th times B to the 20th. Okay. Then we solve for B. We have, first of all, we rewrite this as 80 equals 50 times B to the 20th over B to the 7th. Then that's 80 equals 50 times B to the 13th. Now, we understand the rules of exponents. We'll subtract the power in the denominator from the power in the numerator, we get 13. And then I'm going to write it with the B's on the left, just because that's the way we're used to seeing it. It divide by 50. Then B to the 13th is 1/13th power equals 80 over 50 is 1/13th power. Now you could write thirteenth root of B to the 13th equals the 13th root of 80 over 50. You get the same result. But you just take your calculator, do 80 divided by 50 and raise it to the 1/13th power. Yeah, and I believe somebody punched it into their calculator and got something close to 1.03, right? Okay, now that's approximate. That's not exact. We want maybe another decimal place or two in the 1/13th power of 80 over 50, but I'm just going to leave it with B equals 1.03 and advise you to use at least one or maybe two more decimal points on this, because what you really have here is kind of like compound interest, which we talked about previously. It's like 3% interest. This is like $50 growing at 3% interest. And if it was 3.6% interest, that would make a big difference. Okay. So 0.03 is your growth rate. And that growth rate needs to be a little more precise than this to get a good model. Okay. Again, 3% or 3.1% in the long run makes a big difference. But I'm going to just use 1.03 just for simplicity. And okay, fortunately, everything appears to still be on the screen. Okay. Okay, so B is approximately 1.03. Now we've got to evaluate A. We find A, well, that's really pretty easy once we have B, because we've already determined that A is 50 over B to the 7th. Okay, so A equals 50 over B to the 7th, which is 50 over 1.03 3 to the 7th power. And let's see, 1.06 would be the second power. So about 1.12, but maybe a little more would be the fourth power. And multiply that by 1.06, probably get about 1.2, and then 1.03 times that probably gives maybe 40. Okay? Because I think the fourth power of the 1.03 is pretty close to 1.25, which is 5/4, and we take 4/5 of 50, we get 40. So that's just mental calculation. You do it with your calculator, you're going to be more accurate. But now our model using the value of B and the value of A, be 40 times 1.03 to the T. Now, there's another possible interpretation we could put on this. This interpretation came from fish population that we assumed would be growing exponentially. Another possibility would be you have $50,000 after 7 years. You have $80,000 after 20 years. Then over there so we can see it a little more clearly. Assuming the exponential model, obtain a formula for our principal or the amount of our investment versus time. If we interpret P as your principal, the initial principal, well, yeah, okay. We would get from this information exactly the same model. This will model exponential growth for anything where you got 50 of something after 7 of whatever, days, years, months, okay, miles, and 80 after 20 of those things, okay? So we can answer questions now that we have the model. Okay, well, so we could, if we want to know how many fish we can anticipate at the end of the month, how many fish after 30 days? Well, P of T equals 40 times 1.03 to the T. So P of 30 equals 40 times 1.03 to the 40th. To the 40th, no, it's to the 30th, because we're talking 30 days. Well, what's that going to equal? Started at 7 days, that's 27 days, doubling times about 24 days. So I'd say we end up with maybe 87. You put that into your calculator, okay? Well, wait a minute, whoa. Should be about 110. No, yeah, no. 30 days would be more than a doubling time. I'll say 110, but I don't think it's very accurate. What'd you get? Let's see what people got. Hang on. Okay, I didn't think clearly enough. Well, actually 24 days would be a doubling time. Oh yeah, it's 40 times that. That's why I said, I was gonna say 100, then I said 110. I'll go back to my estimate of 100, but it's like 97. That's more accurate. So. Thought it, but I dropped it. Okay. Makes sense? That's the kind of thing we can do with the model. I could ask you for the average rate of change between t equals 7 and t equals 20, which you could get just from the given information from the graph. Just do a fundamental triangle for these 2 points. Okay. If I want to extrapolate this out to t equals 32, well, this thing's going to go up and up and up, and it's going to intersect this straight line at some point up here. And well, I drew the graph a little too steep because there's 80, there'd be 106. That looks more like 200 than 100, but my graph isn't all to scale. It's not that great of a graph. I want a better graph. I could use our construction technique. And what I would do is I would do a graph. My data points are at t equals 7 and 20. So I want a graph where the window includes 7 and 20. It's always a good idea to start at 0 and use a power of 2, something you can divide into 2 very easily. So if I go from t equals 0 to t equals 32, I've got 8, 16, and 24 here. And now I can pretty easily locate 20. So I'm just debating what color use. T equals 20. Maybe here. And the population would be 7. No, I'm sorry, t equals 20, the population would be 80. So that would be our point on the graph. Okay. At t equals 7, which is a little to the left of 8, population was 50. Well, there's 40 and there's 80. 50 is probably about here.
Obviously didn't know what it was. And then you know it's a picture of me.
We wouldn't use the usual construction of the exponential graph. So I'm going to kind of say, yeah, okay, we can do this. But you've got to be pretty careful how you line off your populations and your times. So I'm not going to go any further with that, but you can do this sort of thing, but you don't need to unless you want a very accurate graph. If you want a very accurate graph, just draw this thing a little more carefully. Okay. The other thing we can do is we can find the doubling time for this function, which would allow us to do something a lot better with this kind of a graph. Okay, so I'm not going to do a doubling time today, but we'll probably do one next time. And you've had problems, I think you had problems where you had to find the doubling time. And it's actually fairly easy. Actually, it's easy enough. I'm going to go ahead and do it. Then I'm going to get to the other thing in a minute. Doubling time you write down a simple equation for doubling time. Whatever the doubling time is, I'll call it T dub. P of T dub equals 2P of T. Well, that means P of T being 40 times 1.03 to the T. Equation not as simple as what I just said. Well, I'm going to write it this way. It's a simple equation anyhow. Okay. Listen. P of T dub is 2 times P of 0. In other words, between 0 and T dub, your population is going to double. How do we solve this equation? First of all, we write it out correctly. P of T is 40 times 1.03 to the T. So P of 0 is 40 times 1.03 to the 0, and we're doing double that. Okay, so if we just write it out using the equation carefully, we end up with this. We can divide both sides of this equation by 40. And we get 1.03 T dot to the T dot equals 2. Now, how do we get that? Well, 40 divides 40, and 1.03 to the 0 is 0. If we just simplify this side, we get 80. And maybe I better do that. Not everybody can necessarily see the step. We get 40 times 1.03 of the T dot equals 80. So 1.03 to the T dot equals 2. So T dot equals log base 1.03 of 2 equals log 2 over log of 1.03, which I'm guessing is around 24. And that's by the rule of 72, which you might have seen. Okay. So pretty easy to see how big T dub is. So now if you want to draw a graph of this thing, you could line it off as usual. at t equals 0, your population is 40. This is going to be your leftmost line. Well, let's not do that. Okay, let's let t equals 0 here. Then your population is 40. If you draw your exponential curve, that means that the t equals 0 line is at t equals 40. That makes sense? Then here, t equals 80, and here, t equals 160. So here's your curve. And over here, well, on this line, p equals 20. And this line down here, p equals 10, the lowest line. But we're really not interested in what happened before t equals 0. Because at t equals 0 is when we invested the money. Or poured in a bunch of fish, okay? Or whatever it is we happen to be doing. So we can kind of say, okay, well, this part of the graph doesn't really matter. It doesn't correspond to any reality that's associated with the thing we're looking at. Now, in other cases, it might be, but in this case, it isn't. Okay, so now we've got this curve. It is a good representation of y equals 40 times 1.03 to the t. Now, the other thing we don't know, well, now that we've got the doubling time, these are doubling times. Every time you go over one line, the value doubles. Okay, so this would be t equals 24. This would be t equals 48. And you'd have negative 24 and negative 48 over here. But since we're not interested in what happened before we started, we don't bother with that. We've got this much of the curve. Now we want to know what p is when t equals, what was it, 30. Okay, well, here's 24 and 48. If we split the difference there, we get 32. No, that's wrong. We get t equals 36. So the t equals 30 ought to be about here. What's p equal on this line? Well, halfway between 80 and 160 is 120, but this is a little bit below 120, right? A little bit below halfway. And p equals 100 is not a bad estimate for a hand sketch graph. So you can see that not only can you find the doubling time, you can use a doubling time to construct a pretty accurate graph. And that's where our construction of the toolkit shape comes in. And if you wanted to extrapolate this beyond t equals 48, you could actually put your t equals 0 over here and label this line p equals 40. So then this would be 80, this would be 160, this would be 320, this would be 640. Now, whether you understand that or not, if you use common sense, keep your wits about you, you can do that. Okay. Well, I do want to move on to the simultaneous equation. Okay, I want to solve this equation by elimination and by graphing. Okay, well, elimination, this would be equation 1, this would be equation 2. If we do 10 times equation 1, we get 20x plus 6y, 60y equals negative 140. Write down equation 2, we get negative 20x plus 5y equals negative 55. Add the left sides and the right sides. The x's go away. 20x minus 20x, no x's left. 60y and 5y, 65y. A negative 140, negative 55, negative 195. We solve, we get y equals negative 195 over 65 equals negative 3. We plug that in. To either equation. And I'll choose the first and bring that down here. And we get 2x not 24, plus 6 times or negative 3 equals negative 14. And here's our negative 3. I'll make that blue because I've circled it in blue just to keep it track, but we don't really need to worry about that. And we get 2x minus 18 equals negative 14. We add 18 to both sides by adding the equation negative 18 equals 18. And we get 2x minus 18 plus 18 equals negative 14 plus 18. So the 2x equals 4 and x equals 2. And I'll put a blue circle around that. We have y equals negative 3, x equals 2. Corresponds to the point 2, negative 3. Now, I can graph this thing, okay? 2x plus 6y equals negative 14. The x-intercept occurs when y equals 0. If y equals 0, 6y is 0, we get 2x equals negative 14. X-intercept would be negative 7. Okay. The y-intercept occurs when x equals 0. So x equals 0, we get 6y equals negative 14. We get negative, we get negative 2 1/3. Okay. 6 goes into 14 2 times, the 2 left over, 2 6s 1/3. Okay. And you have a negative. You go to 20y, 20x plus 5y equals 55. The x-intercept occurs when y equals 0. Negative 55 over negative 20, which is 2 3/4. The y-intercept is When x equals 0, you get 5y equals negative 55. You get y-intercept at negative 11. So we can construct a graph. The biggest number we have for an intercept is a y-intercept at negative 11. So we'll put that down pretty low. The biggest number, by biggest number, I mean the number with the greatest absolute value, the number that's furthest from the origin, is negative 7. So we'll put x equals negative 7 over to the left here. By looking at the biggest, the number with the greatest absolute value on the y-intercepts and the x-intercepts, it allows us to do a reasonable scale. And then we can fit the smaller numbers into that. Okay, so the y-intercept of the, okay, well, here's the y-intercept of the second equation, right? The x-intercept is at 2 2/3. Now, if negative 7 is here, 2 2/3 is probably about here. So there's the x-intercept. And we sketch a line. And we label the line from the equation that gave us the x and y-intercepts. And then we draw a little boundary so we don't confuse it with what we have over here. Okay, there we have a perfectly good line. Okay. We draw the y-intercept for this equation, and it'll go with the x-intercept. The x-intercept is at negative 7. So that would give us this. The y-intercept is at negative 2 1/3. Now, if negative 11 is here, negative 2 1/3 is about a quarter of the way down there. Maybe here. There's the y-intercept. And there's a half decent straight line, more or less, through the 2 points. Now the 2 points intersect. Here. What are the coordinates at this point? Well, the x coordinate that's 2 1/3. 2 would be about here. I'd say it looks like x is approximately 1.7. Okay. Now, if I wanted to estimate an integer, the integer solution probably be closer to 2 than 1. So you probably estimate x equals 2. The y-intercept, if this is negative 2 1/3, this looks pretty close to 3, doesn't it? So this line would be y equals 3, and the intersection point would be the point 1.7, negative 3. That should have been y equals negative 3 because we're below the x-axis. So we have the point 1.7, negative 3. That's our estimate of the solution. We would usually do that first just to make sure if we're going to get a solution that's in the right ballpark, okay? So if we first graph it, estimate the solution, then we have a graphical picture of what the solution means. Then we do the solution, we get x equals 2, y equals negative 3. Well, looks like we nailed the y equals negative 3, maybe just because we're a little bit lazy because it looks like it's maybe a little less than negative 3, okay? And x equals 1.7, which is reasonably close to 2. For hand sketch graph, those estimates are very close, okay? Well, that's one part of it. I'm gonna pause for a second, see if I need to talk about the other part. There's another way to get the solution. And I believe I illustrated this in class last time. It might have been in the co-requisite class, but I think I remember looking at your smiling faces when I did it. We'll see. Okay, this equation, 2x plus 6y equals 4, could be represented, and this is exactly what I said previously. You don't really need the x and the y and the equal sign. All you really need is the numbers, if you understand that the numbers in your first column are going to represent the coefficients of x, numbers in your second column represent the coefficients of y, numbers in your third column represent the coefficients, well, represent the numbers to the right of the equal sign. So if I wrote down, for example, 5, 3, 12, what equation would that correspond to? If we understand that this number goes with x, this number goes with y, and this number is on the other side of the equal sign, it's very easy to see that means 5x plus 3y equals 12. So I can do a little shorthand on these things, 2, 6, negative 14, negative 25, negative 55. I'll put a little dotted line here to indicate that there's where the equal sign goes. Okay. Then I do this, and I call it a matrix. Now we're going to do a little bit with matrices. We're going to learn to multiply them and so forth. Right now, all we're doing is we're going to do what I call row reduction, which is identical to elimination. Except when we do row reduction, we do it a little differently. Now, let me check the time, see how fast I've got to go here. At 6 minutes. We're going to go pretty fast because this is just a preview. You're not really going to have an assignment to do this for a little while, but I want you to see the preview. Okay, so I'm going to call this row 1. Call this row 2. Now, when I do elimination here, I'm going to do it like this. I'm going to do row 1 divided by 2 because I want a 1 here, not a 2. I divide by 2. Divide this row by 2, I get 1, I get 3, I get negative 7. Everybody okay with that? These are just numbers we get when you divide these numbers by 2. You can do that in your head. And row 2, I'm just going to write down. Negative 25, negative 55. Then I'm going to do row 1 just as it was in the previous matrix. 1, 3, negative 7. Row 2, I'm going to do row 2 plus row 1. Try again. I'm going to do negative 20. Now, so I'm going to do 20 times row 1 plus row 2. Now, when I do 20 times row 1 plus row 2, I'm going to write it over here. Okay, here's row 1. Well, no. 20 times row 1 would be 20, 60, negative 140. Because I multiply these numbers by 20, and that's what I'm going to get. Row 2 is 20, negative 20, 5, negative 55. So 20 times row 1 plus row 2 is 0, 65, negative 195. And I'm going to write the 0 here. 0, 65, negative 195. I write this calculation over here. I don't put it below these. All I want to see here is matrix, 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 matrix. Any calculations I do with these matrices, I do it away from the column I'm going to get of matrices. Okay. Then next step is pretty simple. I divide the second row by 65. 0 divided by 65 is 0. 65 divided by 65 is 1. Negative 195 divided by 65 is negative 3, which ought to be familiar because it's a solution for y. And what does this row stand for? No x plus y equals negative 3. Y equals negative 3. We've already solved for y. Now to solve for x, I want 0 here. I don't want 3. If I get a 0 here, then I have x equals whatever I get. How do I get a 0 here? It's easy. I do row 1 minus 3 times row 2. Okay. Well, row 1 is 1, 3, negative 7. Negative 3 times row 2 is 0, negative 3, 9. I add these numbers up. I get 1, 0, 2. This is 1 minus 3 times row 2, which is what I'm then going to write here. 1, 0, 2. And I don't want to mess with this row because it already tells me what my solution. Y is negative 3, right? So this row is good, so I sure don't want to change it. 0, 1, negative 3, meaning x equals 2, y equals negative 3, identical with the solution that we got here, and close to the solution we got when we did the graphs. Okay? You understand that when we get to this, it's going to be pretty easy. Steps are always like they are here, and I would review that a little bit, although we won't get to it for about a week. Fair enough? Okay, so your assignment for next time, in exactly on time, be quitting. Your assignment for next time isn't due until Monday. It's systems of 2 linear equations. And then we'll do systems of 3 linear equations and matrices. And that'll be due like the Monday of Thanksgiving when nobody's here. But hopefully everybody will be here. But one way or another, that's our last topic. And then we have a full week to review, pull everything together. So try to get as up to date as possible. Some of you are, some of you need to get caught up. Life does that to you sometimes. So in the meantime, your assignment for next time is actually fairly easy and should give you the chance to maybe begin synthesizing a few things. Or, you know, if you've got other courses that are pressing on you, it shouldn't interfere too much. I think y'all are in pretty good shape with the upcoming assignment. Okay, very good.